Thank you for coming to my talk. And before I start my talk, I would like to apologize that another speaker cannot come here because he had visa issues. So today, only me will cover the talk, and hopefully I will do the good job. Okay, and welcome again. And I'm very excited to be here to present our work. And my name is Do from TU Dresden. And today I would like to present our system called StreamApprox, approximate stream data analytics using Apache Spark. And this is a joint work between the TU Dresden, the University of Edinburgh, and Bell Labs. So first, let me start with the motivation behind our work. And nowadays, many modern online services make use of stream analytics system to extract the information from the many input data stream. And the input data stream can come from many sources, such as Twitter streaming for the sentiment application, and stream from IoT device for IoT application, and even stream from the stock market for the trending prediction applications. And the stream analytics system in the modern online services is normally have two goals. First is achieve low latency, or sometimes they want to achieve a high throughput in processing the data. And the second goal is efficient resource utilization. However, these two goals is normally contradict to each other. And to achieve low latency, of course, we can add more computing resource, but it comes at higher cost. And fortunately, there is emerging computing paradigm allow us to resolve this tension. The computing paradigm is approximate computing. So what is the approximate computing? So approximate computing is based on observations that there are many applications amenable to the approximate result rather than exact result. For this application, the chain of data is more important than the exact data result. For example, Google Trend application, and as you can see here, nowadays, at least in the last month, people care more about Spark SQL rather than Spark streaming. And for this application, people don't care about the exact how many queries to this topic. What they care is the trend of topics. And for this application, we can apply the approximate computing to tolerate some accuracy to achieve the better latency. And the idea behind of the approximate computing is to achieve low latency and efficient resource utilization. We compute only the partial of data rather than the total whole data sets. And there are many techniques for the approximate computing, for example, sketches, histogram, online aggregation, and sampling. And sampling is widely used in many applications. And in our work, actually, we use a sampling technique. And the idea of sampling technique is for original data, we take a sample of data, we compute over the sample data and provide the approximate resource as well as with the arrow bar to the user. And the arrow bar here gives the sense is how far from approximate result compared to the exact result for the user. So it provides the user only approximate result is will not make any sense because user will not know how far from exact result. And beyond sampling technique, there are many systems have been proposed in literature. And today I would like to present three outstanding work. First is BlinkDB, because you come from Spark community. I'm sure that you know about this system. And this system is proposed by MLab Berkeley. And the idea behind BlinkDB is they perform the sampling offline. And when the user sends a query to the system, as well as the requirement, for example, the accuracy they want to achieve or the latency they want to achieve. And the system will select the relevant sample and process the query and provide the approximate result to satisfy the requirement of the user. And the next system is ApproxHadoop. As the name implies, Approximate Hadoop is built on top of Hadoop. And the idea behind this system is they perform the multi-stage sampling. So in Hadoop, the data is split in multiple chunks. And the first stage, the system will select randomly the chunk. And for each chunk, they perform the second stage sampling to take a sample of data and process over sample data and provide approximate result and the error bar to the user. And the final system I want to present today is the Quoc from Microsoft Research. And the idea of Quoc is they take sampling as an operator in the database system. So they add sampling operator in the query plan and perform the optimization over query plan and execute the query based on the query plan and provide approximate result. So in general, this system based on the sampling is work fine for many applications. However, this system is targeted only for the batch processing, and none of them is designed for stream processing. And this actually motivated us to build our system is a StreamApprox for approximate computing for stream analytics. And when we build our system, we always have three goals in mind. First is transparent property. It means that the user can get benefit from our system by the minor change of their code for existing application. And the second is practical. It means that we provide the simple interface, allow user to make the trade-off between the accuracy and latency. And finally, we want to achieve efficiency by designing new sampling algorithm allow us to take a sample in online manner. So I already covered the motivation behind our work, and now I would like to present the design of our system. So first, I would like to give you an overview of our system. At the high level is input data stream may contain multiple substreams, and we make use of a stream aggregator, let's say Kafka, to integrate all substream to create the input data stream for our system. And the user can send the query and query budget to our system to process the data. And the query budget here can be informed of latency, throughput guarantee, or desired computing resource they want to spend to process the data, and even desired accuracy they want to achieve. And our system, we execute the query over the input data stream and within the budget and provide the approximate result as well as with the error bar to the user. And I mentioned before, the key idea behind our system is sampling. We make use of sampling techniques for approximate computing. And the most widely used sampling technique in the literature is a simple random sampling. And assume that we have the 4 substream, and we present in a different color here. And the figure shows the sampling, simple random sampling have performed with sampling fraction of 50%. And the problem of simple random sampling is may overlook some substream that contain only few data items. For example, the substream in the green color here. So if there is a query specific for the data item in this substream, the system may return a null result. And this is unacceptable for many practical use cases. And in other words, a simple random sampling is not preserve the statistical property of original data. And note that the objective of sampling technique is to take a sample that's representative for the original data. And to overcome this problem is stratified sampling have been proposed. And the idea of stratified sampling is for each substream that we perform the simple random sampling, and none of them will be ignored. So this mechanism will not overlook any substream. And by doing this way, this mechanism can preserve the statistical property of original data. However, both simple random sampling and stratified sampling have to know the population size beforehand. And this may not be the case for stream analytics, because stream analytics, we don't know the population size beforehand, because stream data is unbounded and the stream arriving continuously. And to overcome this problem is reservoir sampling have been proposed. That this mechanism allows us to take the sample of psi k from input data stream. And the idea of reservoir sampling is to take the sample of psi k from the input data stream. Is we make use of reservoir with psi of k, and first we fill up the first k data item. For the k data item for the data item with index k plus 1, it flips the coils with property k divided by I to replace data item in reservoir with arriving the data item. And by doing this way, it allows to take the uniformly the car data items from the input data stream. And there is a math proof behind it, but I will not present it. You can easy to find it in many sources. The problem of this mechanism is actually difficult to implement it in a distributed manner, because we have to ensure the global view of this probability k divided by I. And to build our system, is the first framework we look at is Spark, because Spark is widely used in industry and also in academia. And Spark also supports many applications, many library for approximate computing. However, the library and the sampling techniques that Spark support is just for the batch, and none of them for the stream. But luckily, is in Spark streaming, they consider the input data stream as a sequence of micro batch. So as starting point, we leverage the sampling technique already available in Spark and apply for each micro batch to take the sample of input data. And now let's see how Spark implemented simple random sampling. As the first step, Spark will assign each data item with the values in ranks of 0 and 1. As the second step, it will perform sorting the data item by on the assigned values. And final step, to take the sample of k data items, it will take out smallest k data item after the sorting. And it turns out that the sorting is very expensive, because sorting requires subfolder data around the cluster. Even Spark proposes some mechanism like threshold to reduce the overhead of this step, but it still is bottleneck in stream processing. And now let's see how Spark implemented stratified sampling. As a first step, Spark will make use of group by key function to create strata, and for each substream or each substratum, it will perform simple random sampling. And the final step, it will synchronize between the worker node to select a sample of psi k. But it turns out that each step also expensive, because this step also requires subfolder data through the network. And in this work, we provide a new sampling mechanism, namely online adaptive stratified reservoir sampling. To take similar with stratified sampling, we not overlook any substream, And for each substream, instead of perform simple random sampling, we perform reservoir sampling. And the idea, we make use the reservoirs with the same size k to take the sample of all substream. And we recognize that the data item come from different substreams should not consider equally. The reason that the substream that contribute more data item in original data, we should consider it more important. And to preserve this property, we add a weight accordingly. So the weight we compute by the number of data items have seen so far, divided by the sample size or the size of reservoir. So for example, in the substream at 1 here, is the weight will be the 8 divided by 4. And 4 data item in reservoir here is actually representative for the 8 original data item. And similarly, in the second substream, we add the weight is 6 divided by 4 because original we have 6 data item. Let's imagine that we want to estimate the sum of original data. And to reconstruct the sum from sample data, we simply multiply the value of each data item in reservoir with the weight. Especially in the case that the substream that contain only few data items, even the number of data items in the substream is less than the size of a reservoir. So each data item in reservoir here is representative for itself. And we add a weight equal to 1 because each data item is kind of representative for itself. And by doing this way, we can preserve a statistical property of original data. And at the same time, our algorithm is easy to parallelize and doesn't need any synchronization between the worker to take a sample of data. And let's see how the algorithm works in distributed manner. The figure shows the 2 workers, and each worker will perform our algorithm independently to take the sample of input data stream. And there is no communication between the workers. And to preserve the statistical property of original data is that add the weight accordingly. To implement our system for stream aggregator, we make use of Kafka. And to build our system, we use Spark. And actually, we also build some prototype using Apache Flink. And in this talk, I will present only how we implemented in using Apache, using Spark streaming. So we created a module, a sampling module, to take the sample online in online manner to take the sample of input data stream, even when the batch had been formed. So before we take the sample even before the batch generator. So we can reduce the latency because the Spark streaming, the scheduling, and form the batch for the selected data item, and differ with the Spark streaming that perform sampling after the batch is formed, and we can reduce latency. And we also implemented the error estimation module that allow to calculate the error bound on the approximate result and provide the error bound for user. And this module actually also verify that the approximate result already satisfies the requirement from user in terms of accuracy. And if not, the system will activate the feedback mechanism to redefine sampling fraction. I already covered the design of our system. And now I would like to give you some of the evaluation result. And first, I will give you the result about the throughput with different sampling fraction, and the next is relationship between the throughput and the accuracy, and finally is the end-to-end latency when processed whole data set. And for further results, please look at our paper. And we make use of a cluster with 70 nodes to run our experiments. And we make use of micro benchmark and also do real-world case study to evaluate our system. And for micro benchmark, we also use Gaussian and Poisson distribution dataset. And for first case study, we use the Gaida network traffic trace. And for second case study, we use the network records datasets. And first, take a look at throughput of evaluated systems. And the x-axis, we show the different sampling fraction, and the y-axis, we show the throughput of evaluated system. And the higher, the better. And first, let's take a look on the Spark-based stratified system. As you can see, is a Spark-based stratified sampling system is scaled not very well with different sampling fraction because it requires to shuffle the data to take a sample and require synchronization between workers to take a sample of input stream. And now take a look at our system. And our system is achieved 2 times higher throughput compared with Spark-based stratified sampling, with the sampling fraction is less than 60%. And I mentioned before, we also implemented our system using Apache Flink, and interestingly, with Flink system, we achieved even higher throughput. In fact, it achieved throughput around 1.3 times higher throughput compared with Spark-based implementations. In the next experiment, we keep the accuracy the same and measure the throughput of evaluated systems. And the x-axis, we show the accuracy loss, and the y-axis, we show the throughput of evaluated system. And the higher, the better. And Spark-based StreamApprox in our system is achieved 1.32 times higher throughput compared with Spark-based stratified sampling. And Flink even achieve higher throughput, which is 1.62 higher throughput compared with Spark implementation, with the same accuracy. And now take a look at end-to-end latency. So we also implemented in our algorithm for the key RDD function, and we perform the sampling and compare the performance with the current sampling technique in Spark. So we evaluate this system using the real-world case study. And the figures show at x-axis, we show the name of the system, and the y-axis show total processing time. And the lower, the better. And our system is achieved around 1.68 speed up compared with Spark-based stratified sampling, and around 1.45 times faster than Spark-based simple random sampling, respectively. And now, I would like to conclude my talk. So in this work, we designed, implemented the StreamApprox, the approximate stream processing system, and we achieved the following design goals. First, we achieved transparency, so the user can use our system by just changing one line of code, calling the sampling operator. And the second, we achieve practical. It means that we offer the query budget allow the user to systematically make the trade-off between the accuracy and latency. And finally, we achieve the efficiency by designing a new online stratified sampling technique. And this system is built on Apache Flink and Spark streaming. And if you attend the keynote talk and several talks yesterday, it's mentioned about structured streaming, which is 4 or 5 times faster than Apache Flink. And in the future work, we definitely will try it out. And now I would like to thank you for your listening. And for more details, just check our paper. And now I'm happy to take some questions. Thank you.
Okay. Thank you, Del. We have a few minutes left for questions, so there's a microphone in the aisle. If anybody wants to ask a question. Okay, no questions. Give it up for Doe.